We can start.
Perfect. So it's really a pleasure to introduce our first keynote today, Anna Radovanovic, who is kind of a child of the performance community. She grew up in the performance and sigmetrics world. Got her PhD at Columbia with Predrag Jelenkovic, and then went to IBM for a few years before joining Google, where she is today. And at Google, she's, I think the official role is a senior staff research scientist and technical lead for energy analytics and carbon aware computing. And so that's been her focus for the last 8 years, I think, at Google. But before that, and even during that, she's worked broadly on energy incorporation, decarbonizing the grid, not just cloud, but beyond that in the grid, and has a really impressive background in performance analysis, queuing, scheduling, applied probabilities, stochastic networks, all of those areas as well. So it's really a pleasure to welcome her today. So Anna, I'll give you the stage.
Thank you, Adam, for such a flattering introduction. So hi, everyone. Today I plan to talk about how we do carbon-aware computing at Google. I'll share some insights, opportunities, and challenges that we are facing and that significantly drive how we design and model the systems to do carbon-aware computing. And I'm going to also discuss how we are trying to scale these systems internally and beyond to actually increase the impact and hopefully facilitate grid decarbonization. As Adam says, I'm Anna Radovanovic. I'm technical lead for carbon-aware computing at Google. And the work that I'm going to present today is actually the result of a very, very strong and collaborative effort between team members that are experts in different domains, right, of engineering and data science and energy analytics. So with that, I'm going to start. And first, before I start, I just wanted to thank the organizer, Adams and Danilo, especially, who actually reached out and helped me set this up. Oh, let me just see. So what is carbon-aware computing? So this is exploiting flexibility in when, where, and how computing is done to reduce carbon emissions. Before starting discussing the flexibility, I just want to answer why data center load matters, right? Why do they matter? Why we're talking about this at all? So this is a citation or reference, the result to a work which recently appeared in a science paper, which says that computing resources and data center power have been growing continuously, and now they comprise approximately 1% of total electricity usage overall. And just in the short span between 2010 and 2011, global data center workloads and compute instances, so that the compute usage from data center increased more than 6-fold, which is huge. However, what is an interesting thing that I haven't written in this slide is actually while this was happening, the power usage of the related power usage increased only 6%. Why? Because there was actually in the same time, there was a huge trend and transition from traditional data centers to hyperscale and cloud data centers that are much more power efficient. So for the same amount of compute, we were trying to drive the efficiency down, to power consumption down. So the main premise of the work that we are after and what we are trying to do is that cloud and hyperscale computing data center with some load flexibility can change the load patterns in the grid, electricity grid, and that these changes in load patterns can influence electricity markets and, as a result of it, carbon intensity as well. So talking about flexibility, so there are different types of workloads, and there are some for which there is a flexibility when they can run. And typical examples of such workloads are, when you think and talk about them, this is typically data compaction and distributed computation, right? And we do it to process videos. These are very resource intensive. Then for feature extraction and training of large-scale machine learning models, to optimize for web search, content, and social recommendation systems. Typically, also when you set up simulations, they can run, right? They can run at different times of the day, so you can actually schedule them at a different time, so they're latency tolerant. And there are many other processes that are latency tolerant, and typically they are referred to as batch workloads. And this is an example what can be done. I don't know whether you see whether this dynamic figure moves, but this is what you can see when we shift computing at time. So we can do it in this way so that our goal is, if we are increasing the carbon awareness, we can actually shift them to the time of the day when we can align them better with the carbon-free generation on the grid. And in this way, we can reduce the energy consumptions and the time of the day when there is a lot of which are not really which are carbon intensive, right? On the other hand, there is computing or jobs, workloads that have flexibility in where they can run. And I love the examples and the potential from user-facing services that can be geographically rebalanced and resourced. For example, our requests from Microsoft for cloud applications such as Microsoft Office, Facebook and Twitter messaging, Salesforce enterprise solutions, Google's G Suite, YouTube, Maps, that we use every day, can be served from different locations, right? From different data centers that reside at different grids. On the other hand, also large compute providers can source and allocate pods and compute resources to cloud customers at different locations. And these can be made like carbon aware, and there are some recent announcements of such systems, like Microsoft's carbon aware Kubernetes. And there is also a Google's Cloud Region Picker announced earlier this year, which actually exposes information to users and their cloud customers. And they are actually empowered in this way to choose locations for their hosting their services, which can be more carbon friendly. And we hope to see more of such systems in the future. So this dynamic graph shows how not only that we can be aware and shifting in time, but we can be hopefully, and we are working on that intensively, we can be achieving huge carbon impact by shifting workloads from carbon intensive to less carbon intensive data centers. And the idea in theory is not entirely new. There is a vast amount of work, theoretical treatments, small-scale prototypes, and simulation-based studies that are trying to tackle this and develop approaches and proposals for compute shifting across space, compute shifting in time, data center, grid coupling, etc. So, and I list only some of them here. So what we realized when we were building the system that would work at Google is that we needed a new theory, data, and engineering to accomplish that. And luckily, the flexibility is enabled by several things. These are the key drivers in the development. And this is the accurate carbon intensity data. We have now a few companies that share this carbon intensity data, right? And this allows us to understand what the grid how are the grids powered in time and across space. Then, in order to build scalable solutions, we needed to operate and have scalable infrastructures like cloud. We needed virtualization and migration mechanisms to be able to achieve this the shifting. We needed to understand what is the load that is flexible, and we needed to actually develop optimization approaches and methodologies that would work with our systems, and it would be data-driven. And we have a recent paper that we shared and currently is under review. Here I list a few first deployed systems to the best of our knowledge. The first one is announced in 2020. This is Google's Carbon Intelligent Computing Platform, and the announcements was about our ability to shift workloads in time. Then later that year, 2020, there was a Microsoft announcement on carbon-aware Kubernetes. And then earlier this year, we announced that now this carbon intelligent computing platform is able to actually shift some of the flexible workloads across data centers as well. So what is our vision? The vision is that we can utilize this flexibility to reduce emissions. And the approaches for carbon awareness can be different, right? You can be reporting the carbon footprint to users, cloud customers, and kind of making them understand like what is the impact of their workloads. Then there could be developer facing, because we can be exposing carbon signals, for example, % of carbon-free energy in the local grid, or carbon intensity, right? And they could actually, that can drive their coding designs, right? And scheduling right in time. Infrastructure is something that we are particularly keen on because we are such a large, we have such a large fleet of data centers, and we build a platform for flexible load management that is going to be carbon aware. And also, in order to increase impact, an important piece of work is how to increase the amount of flexible load. And there are so many layers in this, and I'm going to touch on that later. But here, before talking, because majority of the time I'm going to spend on discussing the system for shifting flexible or management of flexible load, I'm going to provide here the screenshot of a system that's a recent announcement. This is what we are able to share with some of the users these days, cloud customers, basically. This is a profile of what is their carbon footprint, right? Per product and services and geographic locations. These are kind of monthly reports right now. Also, this is a screenshot of something of our region picker, which is announced earlier this year. So our cloud customers are able to just go and choose allocations, right, based on their latency constraints and others. They're able, and we exposed % of carbon-free generation in different regions where we provide compute resources, and they're able to choose where they want to be sourced. And now I'm going to transition to discussing the approach for flexible load management at Google. So this is a system that we built. It took us a few years to actually design it and appropriately and build it and prove that it works. But this is a system that actually tries to shape workloads and compute usage and related power usage across all data center fleet, right, globally. And in order to do that effectively, we needed to harness two key things. And this is workload flexibility and electricity market dynamics in the regions where our data centers reside. So, and even before, you ask yourself, what is the potential? And you ask, does it make sense? And what is actually the opportunity? And early on in the development, we realized how much data center hardware how much it can affect power usage per unit to compute down. So depending platforms and machine racks, they can be vastly different in the amount of watts consumed per unit of CPU work done. Also, when we plotted, right, the baseline loads and organic workloads, right, the cluster level usages, and look at the peak power versus mean power usage in a cluster, similarly, this holds for compute as well. We noticed that actually majority of the clusters, this ratio is 5%. It could be large, even larger, but what it gives us, it gives an incentive to actually develop solutions that would reduce these power peaks and increase the efficiency of our clusters and our infrastructure in efficiencies in a way that we could delay. We could use the same amount of machines and CPU capacity for the same amount, or for the even larger demand, right? We can delay the orders, new machine orders, and in that way increase the sustainability of our fleet. And importantly, probably what will drive the major carbon reduction of our compute is this diversity in grid locations where our data centers sit. So these are only three. One is in Finland, one is in Midwest, and one is in Singapore. You can see really the huge discrepancy in intraday carbon intensity values for these three grids, which are powered with different and generation mix. So what were the key challenges and opportunities that we were facing, and what really drew the development of the first carbon intelligence computing system at Google? First, we knew that whatever we developed and are affecting the workloads in real time needs to comply with reliability principles, right? So, like if we are pushing new signals and new controls, right, we need to do it in such a way that when we start affecting load and start doing something wrong to the load, we need to push back, right, to be able to push back in a timely manner. Then we also have hard infrastructure constraints, right? So when we design and guide the load and shift the load, we have to be aware that there is a bound and how much machine capacity there is in a cluster. We need to be aware of the circuit breaker limits. So we don't want to power down a data center and then kill all the workloads and everything that's going on. Then we need to meet the performance expectations of the workloads. So we want to kind of to keep and nurture and keep the flexibility, right? We don't want to harm flexible users as well as inflexible, so we want to actually keep track and actually don't mess up with search, for example. Also, job placements have dependencies and consequences, right? So then shifting load from one location to another, or even in time, we have to be aware that very oftentimes the tasks and jobs are interdependent, and we needed to actually be aware of these consequences. Furthermore, an important realization was that job level resource consumption is quite uncertain, right? And uncertain in for majority of the job types, it's very hard to predict it, especially for the flexible compute jobs. And also scheduler, like previously the approaches previously proposed, at least in the literature, mainly like we're talking about taming and changing the scheduling of loads. And in our case, like we were talking about job schedulers that need to be very computationally light, that need to make hundreds of thousands of placement and scheduling decisions per second. And we don't want to change really the scheduling algorithm. So that is something that we need a huge constraint to work with. So with all of this, what is the approach, right? And what really fundamentally made our approach possible is the realization and discovery early on that the daily amount of flexible compute usage is actually predictable. And I'm going to show some performance results and some graphs very soon. But this is huge because if we know that this amount that is computationally flexible, I can just squish it within a day like a fluid. So it's all about management of this amount of daily compute that is flexible. And we chose the approach, which is actually figuring out what is the load envelope that we could reshape and work with. And that is basically, we wanted to compute the optimal envelope, and optimal with respect to, right, reducing the minimization of the carbon footprint, as well as certain efficiency metrics that I will discuss soon. So in the end, right, we build this new component, and the whole new component in the system, the current system, is actually a suite of analytical pipelines. This was a great approach because we don't mess with existing infrastructure. We add a new piece with a bunch of these analytical pipelines that do forecasting, power modeling, right, and optimization. And the outcome of these running of these analytical pipelines the outputs are basically load shaping guidelines. And you can see them in the red line here. These are curves that are pushed to all clusters fleet-wide, wherever they are, every day. And so if the black line is the organic load, the red line is the line this is the guideline. So what we're trying to do is say, okay, this guideline is actually telling the scheduler to actually shift, right, providing the guideline to shift workloads, compute temporally flexible workloads in time, away from the time and away from locations where the carbon intensity of the local grid, electricity grid, is high. So, and here is a little bit more of explanation of how we do it. So we call these load shaping guidelines virtual capacity curves. And why virtual capacity? Because actually all that we are trying to do is to trick the scheduler. So scheduler now understands how much, when placing jobs to machines, it understands how much available capacity there is, right? And this is this brown line. And what we do is we compute this red line and say, okay, tell a scheduler that it has a lower amount of available capacity at times of the day when the carbon intensity of the local grid is high. So in these ways, believing that it's right, so what scheduler does, it delays these workloads. These workloads are basically go to pending queue and wait for the better time. They're pushed in time later to a later time point. So, and this postponing, so which workloads are postponed? Those that would in general, right, cause virtual capacity curve to be exceeded. At all times, right, inflexible load is not touched. So system is designed in such a way that inflexible load usage is not going to be affected by all of this. So shifting in time, right, happens like at the first come, first in service. Also, it depends a lot on priority, but these are flexible workloads. So we can see how this orange section of workloads are going to go first, and this blue will be happening later or early on the next day when the low carbon intensity of the of the local grid is low. But I wanted to show something else. Yes, we do this carbon-aware computing and shifting and compute these curves to actually minimize the carbon footprint, right? But also, if you observe, organic shape in gray line is now changing such a way that we also decrease the peak power usage. So we can work with two objectives. We can also like not only think about scope 2, right, of sustainability and thinking about electricity-based emissions, we can also like increase the efficiency of the fleet and actually reduce the capacity of machines that is needed to manage our workloads and to meet the demand from our workloads, which is a huge win for Google as well. So effectiveness is mainly due to several, as I said, comes from several points here. The effectiveness is predictability, as I already mentioned. So predictability in the demand, predictability in actually understanding and computing the impact of shifting of compute on actual power usage and power impact, right? Power usage impact. And also predictability of the next day carbon intensity. So the better we know it, and the better we understand how the grid carbon intensity is going to evolve, the more effective we are going to be. There is a scalability point here that we are not, right? We are not changing the scheduler and then we have to think, oh, now it's computationally expensive. How we are going to increase the demand? And for example, if there is the amount of jobs goes, we would maybe probably hit some computational limits here. But we actually plan everything, the shaping in aggregate, and affect this in a way we can, in this way, build the approaches that are synchronized across all clusters fleet-wide. Efficiency and scalability is also important assumption because the same framework we ended up using and expanding since the first implementation. Now we expanded it to actually incorporate guidelines for spatial shifting, portfolio level optimizations, etc. And also an important one because we have SLOs for everything, right? Infrastructure SLOs, workload SLOs, in explicit characterization of SLOs was possible, right? Performance expectation, prediction uncertainty in resource and power demand, and power infrastructure limits, limits set by energy contracts, etc. So this is the architecture of the system that we build. You see there are like different pieces to it. There is a forecasting component. This is run in a highly parallelized manner where actually we manage this daily to do this power modeling that maps the GC or CPU usage of our compute to power usage. Then there is this day-ahead demand forecasting, right? Then there are pipelines that extract capacity constraint, contractual limits, performance expectation that refresh carbon intensity forecasts, right? And then everything is collected and pre-processed and then merged into this optimizer, handed off to an optimizer that does this co-minimization between electricity-based carbon footprint of Google Fleet and peak power usage. The result of these optimizations are virtual capacity curves that are pushed daily to all clusters fleet-wide. These are these guidelines. And obviously, right, we don't know, right? We run this robust optimization framework and like it can do, like in the presence of uncertainty, definitely there is some probability that we are going to harm workloads. And to that end, we have this continuous monitoring, and when we detect that we harmed and violated some SLOs, we have a feedback loop to react to it and keep the system going. So I wanted to show you some of how, like I took a screenshot here from some of our dashboards, and I wanted to show you how these daily forecasts versus actual values, how do they work and how do they look like? And I took actually from I selected a cluster, and on this top graph figure, you see these are the daily demands for flexible compute usage, the one that is latency tolerant, right? And you can see the blue line this is the actual one. The predicted one is the red one. The yellow one is how much corresponds to the capacity we allocate for the flexible load, right? So because it needs to be risk aware, right? We don't work with point estimates. We work with like the safe, like the estimates and the quantities, some quantiles values that are going to ensure that our daily demand is met. And the green line is available machine capacity, so which is taken after deducting the inflexible, right, from machine capacity minus, right, the capacity consumed by inflexible usage. And here you can see below how well we can predict the inflexible demand, because that is important. After all, we are changing, right, the whole load profile. And also again, the actual values are in blue. The predicted values are in red, and like in this case, for example, the median absolute percent error of these predictions are smaller than 8% for more than 90% of Google clusters fleet-wide. On the other hand, I didn't hear mention this global statistics. Median absolute percent error for predicting the flexible compute usage is less than 20% for more than 90% clusters, and in smaller than 10% for approximately 60% of the clusters globally. And then understanding, like when we shift, right? We need to say, okay, so when we shift, we need to be aware that shifting from one cluster, right, or one time to another, how much this delta in CPU usage is going to affect power consumption. And it turns out, and there is a vast amount of literature on the topic, and it's not a novelty that piecewise linear models work extremely well. And interestingly, it can be just a piecewise linear model in just the one feature, which is the CPU usage. That is surprising. That works so well that mean absolute percent error for more, let me see, I think more than for more than 95% of Google Power domains is smaller than 5%. So it's very, very accurate model. And when I say power domain here, I just want to explain what it means. Power domain is just a cluster of racks or a set of group of racks within a cluster. So we have these groups of racks, and they are merged into different power domains that are separately metered, right, within a cluster. Next. Finally, predicting carbon and understanding carbon intensity is the key guideline in how we shift, right? And we early on in the project, we actually, and the project itself, it was hugely impacted by the collaboration with our partners from Tomorrow Company, or they have a very famous website called electricitymap.org, right? And so their 24 to 48 hour ahead of time forecasts are very, very precise and turned out to be very reliable, right? We are actually having these parallelized pipelines that read and refresh values every hour, and that we use to regenerate and compute our next day's virtual capacity curves. Finally, there is mathematics of optimization. The framework is very explicit. Not turned out like predictability and allowed us to actually to design a convex co-optimization framework where the objective is co-minimization between the two objectives to reduce the electricity-based carbon footprint on one end and peak power usage. Right. This co-optimization is right. You see these two parameters, lambda E and lambda P, and we can tune them. They are decisions, right, that we make. And this is something like picking a internal carbon price, right, for Google. And you would say, how well does it work? Do we, like, by co-optimizing, reduce the impact on carbon footprint? Yes, it happens in some clusters, right? But we saw locations where actually, and clusters for which these two objectives are aligned, and they're working for you. Together, they're aligned, and by optimizing for one, we optimize for the other one, and we are able to achieve a larger impact. And these optimizations, as I mentioned, are centralized, performed daily, and they have a fleet-wide impact, right? Since all the curves are really dependent on each other because they're the result of the same optimization, one optimization run, and they are pushed to all clusters fleet-wide. So here are some examples from actual demonstrations from the real system. And what I want to show and discuss a bit is how the amount of flexible load, how the prediction uncertainty, and how the variability and magnitude in carbon intensity forecasts affect the impact of carbon-aware computing. So you can see 3 rows of data taken from 3 different clusters. The first top row shows like the effect of shaping in a cluster with high amount of flexible usage, but also high uncertainty, right? High uncertainty in the flexible usage. So on the right-hand side, you see the impact on power usage, and this black line is carbon intensity curve. So you see that we managed to actually reduce the power usage, right, during this time, very aggressive shaping here, by 8% for 3 hours within the day when the carbon intensity is the highest. However, look at the second examples when the uncertainty in daily amount of flexible usage is lower, we managed to achieve larger impacts. We dropped 88% in power usage at the most carbon intensive times, but for a longer time. So why? Because, you know, when we design and compute these curves, you see this space that kind of is not consumed. This is kind of a machine capacity reservation. But we need to provide it to ensure that the daily demand for flexible usage is met with high probability. And finally, there is the bottom graph where you see the cell with small amount of flexible usage and where actually large uncertainty, where capacity curves has negligible and, you know, like hardly certain, right, impact. Finally, look at this. And this is another way of presenting the impact. So what we did here, we looked at all clusters in the same data center. And then we normalized the power usage, right, of each one. And we are showing in blue lines, and then we averaged out these normalized curves, right, across all clusters within the same data center. So the blue line is the organic shape, normalized shaped. The yellow line is like after shaping, as a result of shaping, and the green line shows you what is the carbon intensity of that day. So you definitely see the impact. You see here that, yes, everyone can say, oh, but this is just 2 to 3% dropped. But let's be aware that this is actually for data centers that have hundreds of megawatts in power consumption. So this is not a negligible impact. However, we are working hard to increase the flexibility and to most effectively actually manage it. So this is the focus of our current work. So what are the challenges, right? And so what we run into is that by changing these lambda parameters and weights, and by trying to be more aggressive in how we load shape, that we started affecting some of the workloads. Some of the workloads, even though they are tolerant, they actually cannot cope well with preemptions. Then understanding the flexibility is also not clear. Like, even if you can exit at any time of the day, how susceptible you are to kind of like delays of 4 versus 6 versus 8 hours. So we are working a lot to understand the impact of shaping and in better characterization of flexibility of workloads. Also, you know, maybe you probably already noticed that capacity curves are very effective, right? If I go back and show you here, they are very effective in pushing workloads away from times when the carbon intensity is of the local grid is high, and from locations where, right, the carbon intensity is high. But we want to actually work on the mechanisms that are going to attract the workloads to locations where the carbon intensity better, to where the carbon intensity, the greenest locations in grids. Finally, there is one fundamental work that we are trying to start and to work, and this is like the impact of load shaping of data centers, especially when we start to scale it, right? And when other people come up with their own carbon aware solutions. How should we do it to actually, and how are we going to impact the actual carbon dioxide emissions from the dispatch generation? And this is very deep topic of optimizing for carbon footprint is related, but not the same is actually carbon emissions of the dispatch generation. So we want to actually more accurately create the link because our goal is to effectively reduce emissions. And this is our message, right? This is the message is that opportunity to do something is now, and that this opportunity we want to share, like we want to encourage, right? And we are exploring even within our own walls. So because in some cases, in some systems, we cannot affect the infrastructure significantly, but maybe we can do something that we can embed the carbon, increase the carbon awareness by embedding carbon signals into cloud products, right? We can be like, this is not new, steering web requests to greener locations, right? But you know, the idea and implementation, it takes some time to figure out how to do that and don't break certain business and system constraints. For us is also like super important how to build tools to identify flexible compute workloads, right? And how to characterize this flexibility, and then how to model it and embed it into utilization frameworks that we have. An important transition that has been happening recently is also in re-engineering software, right, to become more flexible, right, in time, to shifting in time and space, right? So the problem that I mentioned about different workloads react different to shifting and loss in capacity and stuff like that, and preemptions, right? So how we should, what are the appropriate software solutions, and how we should build workloads and jobs to become more resilient and therefore more flexible. Also, like migration, right, to greener cloud region is a hot topic, and we should work also both on engineering solutions and analytics to support this. And finally, like in this world of people asked, okay, this is just carbon aware computing. I don't think that these are the key principles are the same. So what in the world of Internet of Things, right? Why not come up with a carbon aware like management of devices, charging, right? Or for example, thermostats, right? Like the Nest thermostats. So this is certainly a hot topic, and like I think that there is opportunity for both academic research, industrial research, and engineering development to actually converge to good designs and new carbon aware solutions. So I think this is all that I prepared for today, and I'm looking forward to your questions and discussions. Thank you.
Wonderful. Thank you, Anna. That was a great talk. I really like hearing about this. It's such a pleasure to see so many of these pieces that have been studied in academia for a decade make their way in forms and variations. And I mean, the work into putting together a massive system like that can run at the industry level is enormous. So it's really, it's really wonderful to see and learn about. I'm going to take the advantage of being the moderator to ask the first couple questions, but I really hope that others can start to either put them in the chat or be ready to raise your hand, and I'll call on you and let you unmute after I ask a few. So take this chance to organize your questions. So Anna, the first one that I'm really interested in this interaction between the day ahead planning and the real-time planning. I mean, this is something that kind of mimics what goes on in the electricity grid more broadly, but is something that wasn't a big part of a lot of the academic work, at least when things were beginning in this space. So can you talk a little bit about the motivation behind that, and maybe about some of the it was a little bit unclear to me from the talk how tightly that integration happens in terms of the feedback between the two as well, and so a little bit more on that would be great.
Perfect, thank you. So like first, why we need to do day ahead planning, right? Why not, if we understand and we are able to have all this data, we cannot even do model predictive control, update and push and compute these curves, right? Update our forecasts. Well, like as I said, reliability principles, like we cannot be pushing and affecting everybody in real time, because we need to make sure that if we are doing something wrong, we have to push back as soon. So we have to meet certain guarantees in for workload, and meet performance expectations of the workloads. Because even nowadays, with all the feedbacks and safety mechanisms that we put in place, right? Sometimes users complain, especially low priority flexible users. So It's been a lot of learning in back and forth. I said, oh, what are you doing? This is, like, this is this new system, right? And for real time, so this is why the planning is needed, unfortunately, like a longer term, day ahead planning, which is like, we would have been much more effective if we obviously could do and plan less. And we are going and thinking how we could do it, by the way, and come up with solutions to be kind of tighter integration between the real time and day ahead and planning phase. On the other hand, to your question is what is the feedback loop and how quickly we react? So it's not instantaneous for the same reason of reliability. But you see, we are managing load that can tolerate 24-hour delay, right? So, like, and understanding that we are harming this daily demand, we have to have some time need to elapse for us to realize that actually we harmed it, because we need to sum up the demand over the 24 hours horizon. So there is some, obviously, there is no way we could know until we see the 24-hour horizon of data. And luckily, we have data feeds that are continuous, very real time, right? And so once we detect it, and first, the other problem is, like, to your point, how do we know that it's the miss in our predictions, or it's or some just rare event that will happen, and it's not a big deal. It's going to happen, right, because of stochasticity in the process once in 100 days, right? So we have also we keep repeating these checks to make sure that with high probability, we actually correctly identify the violation and we detect with high probability and we prove actually, what we wanted, in order to convince engineers, we need to say, okay, this is the proof, actually see, because these are the proper stochastic processes of these workloads. And with this probability, with probability of larger than 97%, for example, we are able to actually detect that we are actually harming the throughput. And then in that case, what is the feedback to your question is, typically we disable shaping in that particular clusters for 7 days. Why 7 days? Because there are these intra-week patterns. So we want to allow the forecaster to pick up the new trend in load usage.
So that's a very aggressive backup, actually. So it's almost like we need to see one more whole pattern, and I guess that's the risk averseness of this, right? You can't risk hurting people too often, because then the whole idea of adaptivity becomes questioned.
And it is aggressive, you're right. And probably we could do better than this. And we are doing in some cases, right? We're experimenting. You always wish to achieve higher performance, but you have to be super careful, because if you start harming the users are going to actually say, we don't need this system, right? We just
That's right. And so in terms of I guess I'll take one more question. Thank you. I see a couple of questions coming into the chat. After this question, I'll move on to them. The other thing I had, it was kind of around risk awareness as well, is this question of you use the language of optimization pretty much in terms of talking about these trade-offs and these parameterization, but I assume there's some machine learning and AI tools that are being used as well. Are those only being used in the predictions, or are they being used in the control too? And can you talk about that decision making as well?
Yeah. So yes, I am approached with that question very often, even within Google. So we use forecasting, like statistical models to do forecasting. So and only there, right? We use optimization is really like the optimizer, robust optimization, convex optimization, very simple one after you just source and express uncertainties and put them into equations. So, and we get explicit curves, right? Why not use AI or machine learning, reinforcement learning, or any other? Just because of this predictability allows us to have this compact right, framework and methodology, right? If we were to have probably, if the load properties were different, maybe we would have, right, chose another approach. But this predictability and ability to model and express the uncertainty in a compact way allowed us to actually really have an optimization, robust optimization framework.
It's great to hear. Okay, so now I'm going to pass the mic a little bit. So, Monica, Vitalia, you asked a question in the chat. If you'd like, you can unmute now and ask it directly.
Hi, thank you. Thank you very much for the talk. It was very interesting. A lot of nice insights on what you are doing. Very, very interesting talk. My question is how we can involve the users of cloud services in this process. So from different perspective, maybe making them more aware of which is the carbon footprint of their application can help them to make different decisions on how they manage their applications. Or also they can be involved in designing more flexible applications in terms of for instance, helping to define which are the flexible part of their applications or different ways of executing their applications so that they can actually help the decision process on how the applications are managed.
Hi, Monica, you answered the question, right? So exactly that. So I think that finding a way within the specific, right, domain, different systems are different, but first education is important. Also, like, right, exposure to the signals and thinking about how to build flexible, right, workloads and applications. And like, and I'm thinking about anything really. It can be a gaming applications. It can be anything. So just exposure to users and just monitoring. Now I see that in flights, right? Usually when you purchase a plane ticket, you see the equivalent carbon footprint. So there are many ways where I see people react, and I hope that we can increase the awareness to from our actions to actually how we affect the carbon emissions and the climate. Yeah.
So are you planning to give more information to the users about the footprint of their applications? Because you were talking about a monthly report that might be not enough for users, yes, for instance.
Okay, thanks. That's a concrete question. I think that they will get. This is the first launch announced a month ago, right? And it's not a global launch. It's what we announced is just to some customers. And we will be able, to your question, if that is a question, to give granular reporting. This is possible. Also, it would be great even by just exposing the carbon signals and how they change in time to actually probably influence them in how they schedule workloads and when they run them. That would be huge. We also think about these things also in the internally, because we have inflexible, right, compute that we cannot easily shift across space and in time. And we are thinking like, how can we affect, right, this certain like inflexible workloads and pipelines to just run at certain times of the day, right? And to increase when the carbon intensity is low. So, and this is a lot in search and understanding what the workload is, right? But to your point in sharing, yes, hopefully we are going to be able to share more granular information. I cannot talk on behalf of the cloud products, right? Because there are a lot of approximation. Users cannot be traced that accurately. Maybe, and probably they will not also, for many business and privacy reasons, share the power usage in particular. But maybe that will be just the carbon signal for a region where they run their workloads, right?
Okay. Thank you.
I really like the idea of figuring out ways of making inflexible workloads flexible. That could be very powerful. Okay, so another question here in the chat. Russell, would you like to unmute and ask your question?
Sure. Hi, Anna. So when you were describing the co-optimization problem between carbon footprint and infrastructure costs, you mentioned that they often work together. I'm kind of just wondering what kind of conditions do the two fight against each other, because that sets up some interesting optimization problems where they are in opposition.
Yes. So when I say work together, I meant that typically the time of the day when their power usage is peaking aligns with the time of the day when the carbon intensity of a local grid is high. For example, the Midwest US, and there, in the middle of the day, when you look at the generation profile, a grid level, you see that it's a huge amount of coal and natural gas. So this is when, like, by dropping the capacity curves and pushing in, when doing this optimization, we do both, right? We do both. We at the same time, we reduce the power peak and the same carbon footprint because we are pushing the workloads away from these times of the day. To your point, where they work in opposition is when, like, in general, they always have to work, we have to control, right? That, like, if we had only carbon intensity footprint as an objective, we would be able to actually push and compute the curve to concentrate all the workloads, right, in one, it's the cleanest time, right? Which we cannot now, but we need to be aware of, of the capacity, breaker limits, and also efficiency, right? We would never be able to launch something like that if we demand from Google to buy much more compute capacity, right? So, and also demanding is not sustainable options. Why not achieving both, right? But in this way, certainly, like, we are a little bit balancing between the two. Yeah.
Okay,
Great.
yeah, thanks. That's really
Answering your
helpful.
question. Yeah, okay.
Perfect, thanks. And I think actually with that, we're out of time for this keynote session.
There is one more question. Luciano raised his hand. There is also, Luciano, can you raise your question?
Can you hear me?
Sure.
Yes.
Yeah, so we can ask it quickly, and then I think we need to transition to the next session. So
Well,
Luciano, go for it.
Yeah, I thought that I had to, raise my hand, so I did it just after the end.
Sorry, I just didn't see you in my interface.
Anyway, I'm not complaining. I have just two curiosities. One is that you mentioned flexible and inflexible workloads. And can you try to estimate, the ratio between the two? Because I can understand that you can, quote unquote, easily work on the flexible workloads, but there's not much you can do if you want to deal with inflexible ones. If I want to Google something now, I want to do it now. I don't want to do it tonight.
Okay, excellent.
So let me also ask for the second question so that I'm done. So the second question is that you only mentioned computing power, but you said nothing about data management. So if you want to move the computations, probably you must also move the data used by those computations. And, it costs.
Okay, excellent. These are very good questions. So let me first answer the first one. When you're searching, these are user-facing applications. Delays are not tolerable, right? And these we treat as inflexible usage now, right? So the ratio that you're mentioning, there is a quantification, and this was part of our business proposal. We wouldn't be building the system if we didn't have a very significant amount of flexible usage, right? But I cannot I was not allowed to share it even in our paper, right? Because then you can make an implication of how much there is flex and what is the business, right? The business impact of on Google and financial data. So there are ways, but there is a noticeable fraction of flexible demand. And we will be thinking about the mechanisms that I mentioned. Now we are squishing and, managing flexible, because you gain so much learning of how the performance is affected through different mechanisms. You have to start from something, right? And so you start from this. Except that for you mentioned, latency constraints are super important. And finally, the one which you just mentioned is about shifting across space. Yes, I mentioned power implications, and this is our next move. When we start shifting the workloads across space, we are thinking about what are already workloads that are so flexible across space, that have a distributed storage, right, across data centers. So they are such, right? And video processing ones are the ones that we have at Google. So we we kind of starting from applications that are like really prone to and like that are effective for shifting across space. And like the work that I mentioned is like how we can work to enable flexibility is also what we do with storage. Also what we do with the network capacity. Like if we had to balance like communication network capacity, carbon awareness and the cost of additional network to support these services, I think that our decision makers and VPs need to make a call, right? What is for them more important? But yes, to your point, this is cross-resource optimization. This is true. And I mean, for the sake of time and not to confuse, right, everyone, because there is a lot of things that are going on in like building the system for effective spatial shifting. But you are right. Yes, there needs to be cross-resource awareness.
Thank you very much.
You're welcome.
Perfect. And with that, we're a couple minutes over, and I think I'm really thankful for Anna to spend the time with us today. And for those who didn't get a chance to ask questions here, especially for the students and postdocs, remember there's a Meet the Star event on Friday where you could set up time to meet with Anna or any of our other keynotes as well. So please do that if you haven't already. And yeah, with that, I'll hand it over to Zhenghua, who is our chair for our next session.
Yeah.
Thank you, everybody.
Thanks
Bye.
a lot also from my side, and very nice talk, Anna. Thank you.
Thank you. Thank you, Danilo. Thanks, everybody. Bye.